The area of a set of points in the plane is defined in terms of areas of inner polygons and outer polygons. The greatest lower bound of areas of all outer polygons is called the outer area of R and denoted by A upper bar. The least upper bound of areas of all inner polygons is the inner area of R, denoted by A lower bar. The inner area is always less than or equal to the outer area. In case the inner and outer areas are equal, then we say that R has area, and define the value of the area to be equal to the common value of the inner and outer areas. We are concerned here with the existence of area for sets of points under the graphs of certain functions, which we shall describe in a moment. Recall that to determine whether or not a set has area, we must determine whether or not the inner and outer areas are equal. Moreover, in order to prove equality, we have only to show that there exist inner and outer polygons with arbitrarily small differences of area. The polygons used may be very special. For the set of points under the graph of a function, we will need to use only polygons built up out of rectangles, based on the x-axis. We shall consider first the case of a monotonic function, namely a function that is either non-decreasing or is non-increasing. This, for example, is the graph of a monotonic non-decreasing function. When x increases, the value of the function tends to increase or remain the same. Here is the graph of a monotonic non-increasing function. The function values in this case tend to decrease as x increases. This one is also non-increasing and has a discontinuity. Let us show now that the area always exists for the set of points under the graph of a non-decreasing function. We construct inner and outer polygons out of rectangles in this way. The difference of their areas is equal to the sum of the areas of these small rectangles. We can estimate it in this way. The difference is less than or equal to the area of a rectangle whose base is equal to the length of the largest subinterval, and whose height is equal to f of b minus f of a. We are able to stack up these small rectangles in this way precisely because the function is monotonic. Now, by making the subintervals small, we can make the sum of the rectangles as small as we wish. In other words, we can obtain inner and outer polygons, the difference of whose areas is arbitrarily small. Hence, we may conclude that the set of points under the graph of a monotonic non-decreasing function has equal inner and outer areas, and therefore does indeed have an area. An argument similar to the one just completed may be applied to monotonic non-increasing functions. Next, we shall show that the area also exists for the set of points under the graph of a continuous function. In this case, the existence depends on a property called uniform continuity. From the definition of continuity, we know that near a fixed point, C, the values of the function may be made arbitrarily close to f of C by taking x close to C. However, the specification of how close x must be to C may depend on the location of C. Uniform continuity says, in effect, that on a closed interval, the specification may be made independently of the point C. Here is a convenient formulation of this important property. For arbitrary positive number epsilon, there exists a positive number delta, such that on any subinterval of AB having length delta, the values of the function must lie within an interval of length epsilon. No matter how small the epsilon, such a delta will always exist. We shall now see how uniform continuity may be used to show existence of the area. First, let epsilon be arbitrary and choose a corresponding delta given by the uniform continuity. Then construct, as before, inner and outer polygons built up out of rectangles. Using rectangles based on intervals of length less than delta. Again, the difference of their areas is equal to the sum of the areas of these small rectangles. Since epsilon and delta were chosen according to uniform continuity, each of the small rectangles has a height less than epsilon. Hence, the sum of their areas will be less than the area of a rectangle with base equal to b minus a and height epsilon. By choosing epsilon small and taking the corresponding delta, we may make the difference between the areas of the inner and outer polygons as small as we wish. And so, we conclude again that the area exists. It is not difficult to combine these arguments to show that the area exists for the set of points under the graph of any piecewise monotonic or continuous function. Although we have shown that the area exists in some important cases, about all that we know in general is that the area lies between the areas of inner and outer polygons. In another film, we shall define the definite integral, which will provide us with a formula for area and also a practical method of calculating the areas of sets of points under the graphs of many important functions.